All right, just give me a minute here.
I actually went to the and then afterwards, I was like, you know what?
You're already like 9 meters yeah, you're right. Yeah. I what a beautiful city here. I just the gas
All right. Did you guys hear me in the back? Do you want me to put on a mic or is this good? This is pretty smallish room. Okay. Just give me 1 second. Sorry, we're starting late. When I was younger, I used to go to the classroom before our first class to make sure everything works. But now that I've been here a few years, I don't bother doing it. So I was late because this plug is broken. Okay, there's no power up here, and there's supposed to be. But anyway, okay. So first of all, welcome to ECE 60827. That's the number, right? They changed the number to 695. So if you're listening to the videos, it says 695 of the same class. Before I start, who's watched any of the videos that are posted right now? And don't be embarrassed if you haven't. I didn't ask you to do it. I just said you could. Okay, so subset, like maybe like 20, 30%. So I don't know. I think the way that I've run this class in the past, we've had an in-person session and we have the videos. Okay, so some of you are online. Some of you are completely asynchronous online. So you're not even, on the Zoom call. So I have this little owl thing here. Okay, so this is like recording. There's like a synchronous Zoom. Anyone who's an online student can sort of log into that. You guys can log into it too if you want. Some students find it beneficial to be here. I think I like it when you're here because it's more interactive. You can ask questions. You get a lot more out of it, I feel like. But I understand you're grad students. You got other stuff going on. You have to miss a class or whatever. I'm not taking attendance. Everything's recorded. In the limit, all of the material, the core material for this class is already recorded in asynchronous videos. So Purdue dumped a bunch of money at a bunch of us to do like production quality asynchronous videos for online classes to try to like, stand up its online master's program essentially, right? And so basically I took advantage of that and I, it was like recording studio type like lectures, which is basically just me sitting in an empty room. It was actually during COVID, and just like talking to a screen material, which in some ways is maybe cleaner because I don't ramble and I don't get sidetracked by questions, but in other ways it's less interesting because you don't really learn anything other than what comes into my head, which is only a limited subset, right? So it's nicer when there's students and they ask questions and you guys can kind of learn stuff. Several of you are wanting to audit this class. I don't care, that's fine, you can audit. We're not going to grade anything you do though, because when you audit, I don't get resources, I don't get TA resources for every audit that there is. So, you can audit, you can sit here. If you don't want to audit and you just want to come and like listen, I don't care. Like as long as there's room in the class, you can come and sit down. I'm not going to take attendance to get people out. So I had debated whether I wanted to just not go through the slides at all in any of these lectures and just say, hey, go watch the online video. But I don't think that that's actually super productive because I don't know that everyone will. So my plan is to sort of go through the slides, here synchronously. I tend to be a lot slower than the online slides. Some of you took, so I've seen some familiar faces, and so maybe you realize, we definitely go slower in class than the videos. And so what I may do to make sure we cover everything is like, if we fall too far behind, it'll be like, okay, I'm very quickly going to go through this slide set. Go watch those videos for more context. I'm moving on to the next part in class. Okay, so I may sort of speed us up a little bit and use the async videos to give you like additional background. But other than that, I'm going to sort of go through things in order and try to spend time in class on maybe the more interesting stuff. This semester, I'm also going to try to devote some in-class time to talk about the papers that I'll get you to read in more depth. The online videos have a little bit of stuff on the papers. It might be good on the in-person session to talk about papers. You guys are grad students. Even if you're master's students, you should be reading research papers and figuring out what's going on. So I'll try to devote some in-person classes to that kind of thing. And in that line, I'll also probably try to do some additional quizzes that aren't already on Brightspace, okay? All right, so that's just general flow. If you didn't like watch or learn anything about this class before the class, that's fine. We're going to sort of go through all of it right now. Before I start, are there any questions before we get going? All right. Okay, so this is about me. So I am an associate professor here. I started now 8 years ago, which is kind of sober when I look back on it. 8 years seems like an awful long time. It's the longest time I've stayed in any one job, so I don't know what that says. Maybe that I like it, and I do. So I got my PhD in Canada. I'm actually a Canadian citizen. I have like a green card. It's super easy for Canadians to get green cards. I'm sorry, everyone in here who's like dying for one of these from another country. The way the US does this, right, is that there's like, depends on how many people are in line. And if you have a super big country, there's a lot of people in line. Canada, not a super big country. How many people do you think live in Canada? Does anyone have a guess?
100 million.
100 million? That's a reasonable guess. US is 350 million. It's a big piece of land. 100 million seems about right. Any other guesses? 50? That's closer to reality. 30 million. 30 million. I tell this to some of my graduate students, they're like, no, you're wrong. They look at me and say, no, that you're wrong. Like, that's like 2 cities. It can't be that whole country, 30 million people. Yeah, there's 30 million people. So anyway, to get a green card from Canada, it's easy because the line is really short because there's only 30 million people instead of like a billion people. Okay. Anyway, so that's my sort of background where I'm from. My research is in this class. Okay. A lot of stuff that we'll cover in this class is sort of foundations of the things that my graduate students do. I have a lab with it should be precise. I have a lab with 8 PhD students right now and 2 now master's students. So a fairly big group sort of doing research in this space. When I was your age or at your point in your careers, I did a couple of internships. So I interned at NVIDIA and AMD Research, 2 sort of major players in the GPU space. And, I did some work there, got some patents, published some papers, and sort of got some experience on, what industry thinks of research and what industry thinks of how, what's relevant for workspace. And then obviously the things that the undergrads all love, maybe some of you do too, is that I did make video games for a long time. I didn't go straight to grad school as, sort of the typical path for professor is. I graduated my undergrad and then I went and decided I wanted to get a real job and make money. And I didn't really get quite so real a job because I actually just made video games and I worked for EA Sports. And so I made a bunch of these titles. If you want to figure out how old I am, you can sort of date that based on the fact that I made like Madden 08 and Madden 09 and these kind of things. Has anyone played any of these games? Some folks? Okay. What's that?
I played Grand Slam tennis.
Grand Slam tennis for the Wii?
Yes.
Okay. Is it good?
Kind of.
Kind of. It's fun, right? Everything for the Wii was supposed to be accessible. Like, children could play it. What really sobers me is when like I bring this up and then somebody raises their hand and was like, oh yeah, I played that when I was like 6. And I was like, oh. Anyway, so that's sort of my background. And then I teach this class, roughly once every 1 year to 2 years, whenever they'll let me out of undergrad teaching long enough to do it. The other big undergrad, I usually teach 362 or 437 at the undergrad level. And, I teach this when I can get the opportunity. Okay, this should be updated. This is like the 5th time I think I've taught this class. Last spring I taught it. And like I said, I teach these other suite of classes. How many of you in here have taken 565 already? All right, good. Word has gotten around that you probably should take that class first. So I've taught that before. So that is, basic computer, it's advanced computer architecture versus the sort of basic computer architecture that we do in our 400 level classes. So you learn everything there is to know about a superscalar out of order multi-core CPU, and you do a bunch of hacking around in Gen 5 and want to pull your hair out, okay? I generally recommend that you have taken that class before you take this class, because it's sort of, some people jump into this and, maybe they even know how to design hardware, but then as soon as they get a C++ simulator in front of them, they're like, I don't know what's going on and I don't ever want to know. And it becomes a huge shock, right? But if you've already done 565, I promise you the simulator you use in this class is a lot easier to use. Well, I don't know what promise, but generally the feedback I've gotten is that it's easier to use this one than it is to use Gen 5. Gen 5 is like, software engineers kind of went crazy, right? And then hardware designers are like, what is all of this stuff? And, in some ways it's elegant and extendable. In other ways, it's just a huge learning curve for people who really don't care. All right. So a couple notes on this lecture. I really do like an interactive lecture. Like I said, I really have recorded everything already. If you really just want to like sit down and consume content, you don't, I'm not saying don't come. I want you guys to come, but like expect it to be interactive. I think it's better when it's interactive. There's always the sort of online alternative. And if we fall behind because we're just like talking too much, then we can sort of fall back on that. I have office hours. I should update this. This is actually the wrong times. I posted the right hours on Brightspace, and I'll post these slides too. I haven't posted all the PowerPoints, but I'll post them all after today's lecture. I am going to, so it's not possibly, I will offer office hours online as well. And depending on how many online students end up taking it, for those of you who are listening online, there may be like a separate time that's maybe outside of work hours. A lot of our online students actually have real jobs and can't show up at 10:30 on a Tuesday. Okay, don't email me for course questions. Please use Piazza. Myself and the TA monitor this, and plus everyone else gets to benefit from discussions there. All right, so what are my goals for this class? I'm going to give you some practical programming experience. This isn't a pure mathematical class. This is not just a theoretical class. You need to get your hands dirty and code some stuff up. And so what we're going to do is we're going to spend a few weeks, a month-ish, on trying to understand how to program a programmable accelerator, right? That's sort of the name of the class. So let's program these things. And the programmable accelerator we're going to use is a GPU, which, if you haven't noticed, is the most popular programmable accelerator, which we'll get into in a minute. And the thing you need to know when you're programming these, especially if you want them to run fast, is that you actually have to have some knowledge about how the architecture works. If you are a machine learning developer, you just write stuff in PyTorch and you build your neural nets and you connect them all together and you train it on a bazillion, gigabyte data set, and you never know what's going on the GPU, right? There's even a flag, right, that says like use CUDA, and if you have a GPU, it'll use it, and if it doesn't, it'll just use the CPU. Like, you don't need to know how the GPU is working to code in that. That's not the level that this class goes into. Think about the person who has to like code out the back end for all of that to actually take you know, these things that are sort of high level, break them down into, you know, mathematical operations, break them down into individual kernel computations, and then schedule them, run them on the actual machine, and then get that machine to actually run fast. That is the level of detail that we'll get to in this class, okay? And you'll have lots of sort of practice programming there. Again, I try to balance it being practical so that you get good experience and then just being too much work, right? Because, you know, I could just like flood you with stuff to do, but I try to create a good balance there. Sometimes we hit it, sometimes we don't. It just depends. Okay, so the first part is learning how to program these things. You're going to practically do it. We're going to talk about the programming model, give you sort of an overview of how this works. So very good nuts and bolts on how to use GPUs. Some people actually just take this class only for the first part. They don't care about the architecture. They don't want to be a hardware designer. They just want to know how to program GPUs and make them efficient. The second part of the class is going to go into the architecture itself. So more 565 like, right? I don't start off with sort of the architecture because most people, who's programmed a GPU before? So we've got maybe like, let's say 5%, 10%-ish. So it's a minority. It's actually grown, right? When I first started this class, it was like nobody, but obviously they've gotten a lot more popular to use. Some of you are probably using them in your research to do something. If you're a graduate student, especially if you're working on machine learning or something. So, you know, there is more expertise, but, you know, when you start 565, everyone's written a CPU program before, right? You know how a serial program works. You don't know how a parallel program works. So that's why we sort of do this stuff first. And then we segue into the architecture. We look a lot more at the microarchitecture of this thing. How does this differ from a CPU's design? What are the design trade-offs here? Read some papers on some stuff that has not been implemented in actual products, and understand some of the design space, some of the work that goes on in architectural exploration in this space at the sort of hardware level. And then the last part is actually on other types of programmable accelerators. So GPUs are not the only game in town, particularly when we're talking about something like machine learning. This is a huge space. The space is growing. We cover a limited subset of that in this class. You know, ideally, we'd have a whole other class on just like other types of crazy machine learning accelerators. But right now, it's sort of a third part of this class. And, you know, I think that this is probably still the right way to approach this because the bottom line is the thing that accelerates machine learning the most today is still GPUs. And we'll see some consequences of that in a second. All right, so what is my overall goal, besides these very specific objectives, is to make a very useful class for you guys that is not an excessive amount of work. I think generally the first part people agree with. The second part sometimes is more work than they had wanted to put in. We've tried to mitigate that a little bit by making some segments of your programming assignments a bonus. So basically the core stuff is what you'll have to do, and then the stuff that sort of stretches you and maybe takes more time is actually bonus, and you can use that to make up for, you know, not doing quite so well in the quizzes or not doing quite so well on the examinations, okay? So a way for people who are interested and have the time to do more stuff, but not kill everybody and still have them, you know, enjoy this class. All right, so what is a programmable accelerator? So before I start, actually, any other questions here? All right, so basically, hardware acceleration itself is really everywhere. There are all kinds of different components that are, you know, customized ASICs, fabbed into SoCs, for example, that do very specific tasks, right? Video encoding and decoding, you know, machine learning specific accelerators, the sort of, you know, NPUs you may have heard of, right? These are hardware accelerators, network accelerators, cryptography accelerators, Bitcoin mining. The best way to mine Bitcoin is with ASICs, right? You can't actually run them on programmable things because the power actually doesn't work out in your favor. And now even, you know, ASICs aren't really all that profitable in that space anymore either. But hardware acceleration is sort of different from programmable acceleration. These things are like very tailored to one specific task. Programmable acceleration is more flexible, okay? And that's what we're focusing on in this class is programmable acceleration, which is essentially what the GPU is. So you can design efficient hardware to solve a lot of problems, but to add that extra level of programmability so it could solve, you know, really any problem. On a GPU today, you can pretty much run any program that you can run on a CPU, except that if it doesn't fit the GPU's model very well, it's just going to suck performance-wise, but it'll still run, right? It's programmable in that sense, and you can sort of evaluate that trade-off of like, well, how much worse is it on the GPU? Is it worth it for me to use this on the GPU, et cetera? Right, so any kind of like bespoke, it's this kind of fancy English word that means it's like, it's sort of it's set in stone, kind of, I guess is one way to think of it. Accelerator is not necessarily programmable. We're focusing on stuff that is, you know, Turing complete for the most part, which is what the GPU is. Okay, so they are, basically arbitrary C code, which is essentially what CUDA or OpenCL is, can be executed on this thing. Now it's not always going to run well, like I said, but it is going to work. Okay. All right, so here's this little, two-dimensional thing I like to show as like a broad view of, programmable acceleration, hardware efficiency, and how the sort of space looks. So if we think about two axes and we start trying to plot different types of machines on these axes, you can think of like, well, how easy is the thing to program on the y-axis, and then how efficient is the hardware on the x-axis? So at the uppermost point here, so if I was going to go, do I have a pointer? Do I have a pointer? I already did. So here at the upper left, your upper left point, arguably the easiest thing to program for the programmer, not the hardware designer, but actually has the least efficient hardware, is a single core out of order superscalar CPU, right? Why is this the easiest to program? Yeah.
Single thread.
Single thread, you don't have to worry about parallelism. It's still sort of fast though, right? Why? Why is this thing sort of fast? Yep.
Microarchitecture implementations like pipelining.
Pipelining. What are some other things that are in an out of order CPU?
Tomaso's algorithm.
Tomasulo's algorithm, which does what?
Overlaps execution.
Overlaps execution. Anyone got a better answer for Tomasulo? That's a good answer, but what does an out of order CPU do? Yeah. Instruction level parallelism. I have a serial program, back some of you from 362, right? We have assembly instructions. They're like one stacked on top of the other. This is supposed to happen before this. This is supposed to happen before this. An out of order superscalar CPU says, yeah. I understand. This is how you want the program to run. I'm just going to run it in whatever order makes it the fastest. So it basically takes a look at that serial stream and then tries to extract as much parallelism as it can from it. Some of that's through excessive pipelining, so there's more than one instruction in flight at once. Some of that's through out of order execution, meaning that even if this instruction was supposed to be issued first and this one second, if there's actually no dependency, then maybe I'll just issue this one first. Okay, so at runtime, the machine is like looking at all the dependencies and saying, well, what can I get away with? And then it goes a step further. What does it do a step beyond that? Even beyond just sort of like reordering things, what does it do in addition to this? What can screw up out of order execution that you need to do something to fix?
Branch prediction.
Branch prediction, so speculation. Okay, branch. So branch is an instruction, a control flow instruction. You don't actually know which way the code's going to go. But, I can make a pretty good guess. Turns out they're pretty predictable. So you can basically build a branch predictor to say, I think it's going to go that way, and then I'm just going to start betting on that path. And then I'm just going to keep going until I figure out if my bet is wrong or not. And then if I'm wrong, I have to basically roll things back. So all of these things sort of make your stupid code, right? Your very serial code that has no explicit parallelism in it, that was written by someone who just didn't really want to think about what system it's running on. They're trying to make it run fast. But all of this stuff saps efficiency. All of these things need to be implemented with something called CAMs, content addressable memory. These things are really, really power hungry. Every time you speculate and are wrong, you're throwing away work. These are joules of energy that you're spending on stuff that is not explicitly doing flops, right? What we care about, especially in scientific computation or machine learning or whatever, is like, how many operations do I get out of this thing? All of that fancy stuff that I put in the single quarter out of order core is sapping energy that could go to just pure computation. If the program was sort of specified with the computation in a much more explicit manner than it is in this out of order stuff, okay? So it's really energy inefficient. You cannot, if you're going to add all this fancy stuff, it's going to cost you something that you're not spending on sheer floating point operations or sheer mathematical operations, okay? What do you think the other extreme end of this is? So I've got like really, really good hardware efficiency, but it's really hard to program.
ASIC.
And ASIC, okay? Many of you probably design ASICs, the VLSI group right here, some folks. And for some of us, actually, you know, it depends on your background, I guess, because, you know, maybe it's easier to write RTL than it is to write C++. For some students, that may be true. For the general world, it is absolutely not. Okay, if you look at all the computer science graduates that are graduating at the, you know, rates of thousands, you know, in every state every year, they're not going to want to write all of their programs in RTL, but they're okay in Python or C++ or whatever. This is way easier to program than this, even though maybe to you, you'd rather write RTL. Even if you were honest with yourself and you spend a little time to understand C or C++, you could probably admit that, yeah, it's easier to like build a program that does something in C than it is to do it in RTL, I would think. Maybe some of you disagree, but generally it's really hard to get things right and debug them and actually, you know, go through the whole flow to take this out as an ASIC. So you could have every unique program that you've ever written, every .exe, every whatever, every .so that's sort of, you know, bundled together in Linux to an executable. You could make a customized ASIC for that, right? You could just, like, in theory, you could turn that into a piece of hardware. There are such mechanisms that do this. High-level synthesis is an area that basically tries to do this, right? You write some C and then it turns it into actual hardware at the end, which is a god-awful mess and never really works very well. Sorry to those of you who work in that space, but it's generally something that's been a holy grail. But I could, in theory, make a much more efficient piece of hardware if I just curved it exactly to the program I cared about. But it's really hard to do that in the first place. It's really hard to produce that, and it's really hard to even write the RTL to do it in an efficient way. And then there's sort of some spaces in between. So if you go to multi-core, this gets harder, right? Who's programmed in a parallel language before with threads, for example? Most folks, right? I think probably our undergrad degree gives you this at some point: pthreads, OpenMP, MPI maybe. So again, you're still running on a CPU. It's still trying to make the serial parts of your program run fast, but now you've got to deal with like cutting the program up and distributing the work to threads. And then what is the hardest thing about doing this? Synchronization, right? Because now you have like all of these independent things flying off, doing whatever they want, and then you have to figure out where they butt up against one another and coordinate, make that efficient, make that actually work well, right? The first time you parallelize your program, it probably doesn't even function correctly, right? It's like wrong because two of them are trying to write to the same address, or one of them is waiting on the data the other one was produced and you never actually waited for it. And you have to like look at every individual program and orchestrate that synchronization. So it's a little bit more efficient because, you know, we maybe don't devote as much space to all this out of order stuff. We just like plunk it into a bunch of different cores. And you can go to the extreme here to make a bunch of in order cores, right? And make them multi-threaded. But it's harder to program because now I have to deal with threads. And then a GPU is arguably somewhere around here. And maybe this diagram is a little old. Maybe it is getting much easier to program than when I sort of first made this thing, but it's a lot more efficient because it throws away a lot of the things that were in your CPU. A lot of the things that made that code that was sequential run fast get tossed in favor of stuff that just does pure computation or that facilitates really highly parallel execution. And when we start sort of looking at the microarchitecture of these things, that's what we'll notice. Everything here is about throughput. Single-threaded latency, who cares? We're going to make memory accesses like 10 times as long as they are on a CPU. We're going to miss the cache all the time. Who cares? That's how the GPU is going to be designed, because it's going to have so much work that the programmer has specified in thousands and thousands of threads that we're going to be able to hide all of those latencies. And the only thing we care about is how many threads we can process at once. Okay, but it's harder to program, right? You can't just pound out your C program and have it work here. You still got explicit set parallelism. And as we take a look at the programming model, we'll sort of see how that works. And generally, the space of, the sort of research that I do and a lot of folks, are doing and have been doing is sort of trying to move up here, right? This is up and to the right is always better, right? It's like a financial thing. You want to, over time, you want to get more valuable. It's easy to program and the hardware is efficient, that's sort of the holy grail, but these things often are sort of competing with each other. And this trade-off is really part of the thing that, my team explores in our research. All right, why study these things? So, on a research front, if you're doing computer architecture, general purpose programming, like CPU-based, out-of-order execution, on a single thread basis, so ILP extraction, branch prediction, value prediction, all these different types of techniques to try to do, register renaming dynamically, et cetera. We've spent 30 years with hundreds of super smart people and billions of dollars trying to make this better, and we did. But it's diminishing returns at this point, right? The amount of ILP you can extract from programs has arguably reached, a point where, you look at papers that study branch prediction and they'll get like 0.5% performance improvement, right? And you can argue that, well, it's on general purpose programs and it's over 40 programs, but 0.5% is still 0.5%, right? You're not getting the wins that we were in the early days. And that doesn't sound good to investors. That doesn't sound exciting to researchers. I did my PhD and I got 0.75%. Okay, good, yeah. But it's not as exciting as the field that of programmable acceleration where it's less well trodden. Okay. This is sort of a relatively newer field. GPUs have not really taken off as general programming devices outside of, 10, 15 years ago is when it started, where you think about CPUs has been going on, since the 80s or whatever. You want to read really interesting, clever papers about CPUs, you go back to the 90s, right? There's all these like really nice ideas in there. There's a wide open field and they sort of found the good stuff. And then now it's really hard to make continued innovations on that very, very built up tip. And there's some arguments, about how far we're actually going to be able to go. On the other hand, we're still actually getting more transistors. So despite sort of claims and reality that Moore's law has either died or slowed down, right? What does Moore's law say? Who can recite to me what Moore? This should be like your Bible, right? I mean, you guys are like graduate computer engineering students. What is Moore's law? You can't answer. You've already answered your exam. Yes.
The number of transistors on a chip doubles every 2 years.
Close.
18 months.
How long does it take? 18 months. So his conclusion was that the number of transistors that you could economically fabricate on a chip would double every 18 months. Okay. And that was just purely empirical, right? Moore is a chemist. He's not a computer scientist. And they worked at Intel, basically as one of their brain, like analytical children. And he basically did this plot of like years on X and then number of transistors on things that have actually been built and sold on Y. Okay. And then if you looked at it, it was exponential and it was doubling every 18 months and it just held. And this was not, part of this was scientific, right? Because we were actually able, the science was getting better and we were able to shrink things down. And most of this was economic. Because we were actually, improving manufacturing processes. There was intense competition that if I didn't double in 18 months, they would. And in this industry, if you're not faster or bigger or better, you are dead, right? So the sort of economics of this drove Moore's law to sort of double every 18 months. And now that has definitely slowed down. If you looked at that same plot, we're still doubling. It's still arguably exponential, but it's not 18 months anymore. It's maybe more like 24 or something, right? It's slipping. And the reason is we're bumping up against physics. Eventually you get so small, it's really, really hard to make them smaller. And then maybe you can, but guess what? It's not worth it economically anymore, right? It's maybe really nice to make like 0.5 nanometer, transistors in a lab and say, look, I did it. But if I can sell 5 nanometer at a much more economically viable rate, because I can't actually clock these things any faster, and I'm not doing much more with all that compute, and it costs me so much more to build the fab for 0.5 nanometers, then guess what? I build 5 nanometers and I'm done. As soon as the economics collapse, Moore's law collapses. So the point of the story is that, in both the CPU and the GPU space, we still are getting more transistors. GPUs are getting sort of bigger, faster than CPUs. And there's other examples of accelerators like in machine learning that have like stupid amounts of transistors. Who's heard of Cerebras? Some folks, anyone who took my 565 has heard of these guys, right? So what is their shtick? What is their claim to fame? What is the thing that they're doing? Yes.
They have like a computer that's this big that has 800,000 cores and it consumes 22 kilowatts of power.
Right. So they're using a technology called what?
Wafer scale.
Wafer scaler. Okay. So your chips in your GPUs and your laptops, whatever, they're basically, sort of the area, I don't know the exact numbers, but they're sort of like this big, right? If you ever rip anything off, they're some number of millimeters squared. How those are produced is that we basically got these big silicon ignats. Okay, we cut them up into slices, you get this sort of wafer, and then we stamp the wafer and etch the wafer with the particular patterns of that chip repeatedly all over the wafer, and then we cut them up, package them, send them off. Okay, and then you get a bunch of little chips out of this sort of big wafer. These guys said, no. We're not going to cut it up. We're just going to like stamp the whole chip design on one giant piece of this pie and call that the chip. Then we're going to package it, figure out a way to give it enough power and cool it, and then call that the wafer scalar engine. And as a result, the thing is huge. It's sort of jury's still out on whether this is useful. They certainly have gotten VC money, and people work there and they do stuff. But will they actually, end up, taking down NVIDIA? I really don't see that in the cards. But it's super interesting and sort of this, they're sort of pushing the boundary of this space. Most of this is actually SRAM, right? Like most of this giant high plate thing is just on-chip memory because, well, you can store more weights on there when you're doing machine learning computation, and that turns out to matter a lot to not have to go off chip to get the weights. So I just dump a bunch of SRAM in there. I have this sort of systolic data flow thing inside, and then off you go. And then I just use software to basically program it. That's kind of the idea. But it's super interesting, and there's all these articles on them because you can sort of hold the chip and it looks like a plate, right, that you put dinner on instead of like a typical microchip. So Moore's law is sort of turning on in both the GPU space and then some of these outliers as well that sort of have giant amounts of transistors. And it was economically fabricated, right? I mean, Cerebras exists. They made the thing. They sell it. So there's sort of a point on that super high curve. So anyway, the sort of point of this overview of why you should study this is that the future is in acceleration. I wrote these slides like in 2017. And I think that, it's not even just the future, it's today, right? Today, what's driving a lot of growth and a lot of interest in the hardware field is acceleration, okay? So I can say that, but how can I prove it? I always like to put up this slide every time I teach this class. So what I've done here is I'm plotting on the x-axis years, and I'm plotting on the y-axis the market capitalization of NVIDIA. What is market capitalization? What does that mean? When I say market capitalization, who's some finance wonks in here or on their phone like trading Bitcoin every 5 minutes? What market cap mean? Yes.
So outstanding shares multiplied by the total stock.
Outstanding shares multiplied by total stock value, which in layman's terms, this is how much your company is worth. Okay, stock price is a function of like how many stocks you have. You can split your stocks and then cut your stock price in half and have double the amount of stocks. It's just meaningless. What's meaningful is if I sold all the stocks in this company right now, how much money would I have? That is market cap. Okay, so that is the super important number. Now, unfortunately, Google Finance doesn't give me market cap, but since NVIDIA didn't split that much, or even at all, maybe they split a couple. Those are not splits. Those are events.
No, there's market cap on the right.
No. Market cap is there. I'm going to get there, but this thing is showing stock price. Okay, the graph is showing stock price. It loosely follows market cap, okay, because they didn't really double or triple their shares over their period. All right, so market cap. This is important. This is how much the company is worth. Based on this slide, how much is this company worth?
1.34
trillion dollars. Now, in these large numbers, and if you're not like super into finance, you look at this and you're like, all right, sure, sounds good. Like, what does that mean, right? 100 billion, 100 million, 100 trillion, I don't know. Like, it's all big numbers, right? So, two things here. So one, that sounds like a lot. Maybe it is. Let's look at some comparables. And the other thing is that, they existed for a long time, right? They existed in the 90s. What did they do? What was the primary driver for NVIDIA's market share in the 90s, early 2000s, et cetera? Where did they make their money? Right? This isn't a bad company. I know it looks like it's close to zero, right? Now it's still alive for this whole period and probably worth more than, half the companies in the world. What were they selling when it was flat like this? GPUs for what? For video games, right? So who's bought a GPU to play video games? Some of you, fractions of you. There's GPUs in who's ever played a video game? Some folks haven't played any video games. GPUs are sort of fundamental to playing video games. You ever played a Switch? If you ever played, even on your phone, right? There's like a little integrated GPU in there. Okay, so in the early days, there was no such thing as a GPU. That's why the company was born, right? There was no specific piece of hardware that could do rendering super well. So they essentially, bought a couple companies and created, what today is NVIDIA. And that was their market. Was they were selling these to gamers. Okay, they were commodity market because gamers are kind of relatively poor. Right? They're not the U.S. government. They're not Google, right? They're like a 13-year-old kid who wants a GPU for Christmas. So they have to be affordable, right? They have to be a few $100 or else you're not going to sell any of them. So they had to make them cheaply and they had to make them work well. And they were the sort of the big dog, right? There was another big company called ATI that was also making GPUs at this time. They ended up getting bought by AMD. And, they're still sort of part of AMD's. AMD's GPU line is, a carry forward of that. So during this time period, they're sort of selling GPUs. They're, doing okay, but they're not like, they're not obviously on this huge spike that we see later on. Let me see if I can get this up on here. I should have brought a PowerPoint thing. Now I'll just point. Okay. So then things sort of start. So CUDA, when was CUDA introduced on this graph? Does anyone know? When was like CUDA 1.0?
2014.
2014? No.
2008.
What's that?
2008.
2008. Yes, good. So I don't know precisely the date. All I know is that I started grad school in 2010 and they were already on CUDA 3. And then I worked that back 2008 sounds about right. I think it's around 2007, 2008 timeframes when it got released. They worked on it a little bit longer, but that's sort of when it got released. So CUDA was there, right? So you could program these things to do, what does CUDA allow you to do in a GPU? Spawn kernels, basically write C programs. If you want to use a GPU to do graphics, you have to code in something called a high-level shader language, OpenGL, DirectX, okay? So when I worked in video games, like you'd write these really weird-looking programs that were like shaders. They were like in the shader language, and it was like, okay, these very specific operations trying to figure out what colors should be on the screen, okay? And then you couldn't actually just run like a C program on these things. And so the smart people, like even before CUDA was invented, were like, hey, this is actually like a really highly parallel processor. What if I took my matrix and I turned it into a texture, which is basically like an image in graphics rendering. And then I threw that thing at the GPU and told it to render, but then instead of rendering the output image, I was just rendering my output matrix, right? So I'm gonna hack the software to make math look like images and then take the output image that is the result of my math and then call it the result, okay? And if you're clever enough, you can make that work, but it's a huge pain in the ass, okay? It's really hard, it's not amenable to like giving it to anyone to program. You really have to know graphics rendering and how the hardware works and how to interface with this. So then they looked at this and said, yeah, this is maybe a good idea. Let's provide a general purpose programming interface for these things. And so CUDA was born, which is basically like a very limited subset of C that you could use to spawn kernels and run general programs in GPUs. So this is 2010. So it's out there. People can actually use GPUs to do all kinds of weird, interesting things. It's got some traction actually in the US government, in things like national laboratories. Big agencies are maybe buying hundreds of these things. That doesn't really affect your stock all that much. It maybe keeps you alive. But then what happens here sometime around 2000, like this is around 2016, 2017, what happens? Sorry? Convolution neural net. What is this sort of, when anyone says what started the sort of machine learning, CNN, image recognition revolution, what's the word that comes to mind? AlexNet. Who's heard of AlexNet? Some folks. We'll talk about this later in the class. But basically, for a long time, machine learning has been around for a long time. AI has been around for a long time. It just didn't work, right? I mean, it sort of worked, but it didn't work great. And then in this, I can't remember, AlexNet was like 14 or 12? 12, it was 12. So there's a paper, AlexNet comes out. There's this competition on this thing called ImageNet, where they basically give you a bunch of images and you try to say whether they're cats or dogs, or it's more complex than that. Like, is this a Yorkshire Terrier versus a short-haired poodle or whatever? And they have a competition. You try to figure out, who's got the best accuracy. Okay. And so then there are all these different machine learning techniques that are being used to try to figure this out. And then these guys from the University of Toronto, one of them, Alex, what's it like, Kriskishov, it's an Eastern European name. Jeff Hinton, who's heard of Jeffrey Hinton? Some folks, he won the Turing Award, which is like the biggest award in all of computer science. For like, essentially, he's, generally credited with spawning the machine learning and AI revolution because of his work on AlexNet, which was actually mostly his master's student. It's like a side project of his that his master's student sort of, brought to fruition. And he named it after himself. That's why it's called AlexNet, because his name is Alex, whatever. So anyway, this thing comes along and it's way accurate than everything else. Okay. It's using a convolutional neural network, which is a type of machine learning network that we'll cover in this class. And it does way better than all of these classical other AI algorithms. And the way that he did this was by using CUDA, okay? There was no such thing as PyTorch. There was no such thing as like cuDNN and all this back then. He basically wrote CUDA kernels to do, essentially neural network computations on a bunch of GPUs. I think it was like 4 or 8 in the original paper, right? Like some cluster that like his lab supervisor could buy, not like that's sitting in Google somewhere. And he trained it on a whole bunch of data, and it could churn through the data very quickly because it had many parallel cores in the GPU. And then the thing ended up being way more accurate than anything else. Like, I can't remember I had the numbers in here somewhere, but it was like, this is what the last 30 years of AI research has given us, and like, this is where AlexNet is. Just a huge jump in accuracy. And nothing super clever, but like, no, like complicated algorithmic, deep AI thing. Just I threw a ton of data at a GPU with a neural network on it with this particular configuration where I sort of slide some filters over the images and then do this in a number of layers. And I just trained it a bazillion times with reinforcement learning. And this is the end result. It was much better at machine learning. And then it was much better than all these other previous things. So anyway, that sort of happens around here, man. I had taken a long time, but that's okay. That sort of happens in this time frame between 15 and 20. Okay, the machine learning happens, it's maybe better, and then people start to pick up on it, right? That, oh wow, this is really good at image recognition. AlexNet now is like behind where they've been able to come, because as soon as people decided that this was a better way to do things, then deep learning, which is basically like huge multi-layer neural networks that you can train, sort of took off and took on all these interesting flavors. It's where, ChatGPT, right? You've all heard of this, probably your students. Right? Generative pre-trained transformer, that's what GPT stands for. It's sort of, all of this sort of stems back from, this sort of deep learning phenomenon of having this neural network with multiple layers that you could actually train, okay? And then it sort of explodes. And what's great at doing this deep neural network training? GPUs, okay? They're there. They're pretty damn cheap because we made them cheap so that gamers could use them. And everybody needs them now because now every space needs some kind of AI. Try to build a company today, make a pitch to an investor and not have at least an answer to what about AI? It is the hype child of today, and with good reason, right? There's a lot of things that it can do that are super impressive that sort of justify its hype. So anyway, that kind of happens, and then things explode, okay? They just explode, and they kind of, there's some dips in the way, there's COVID in there, there's, market downturns, but they just continue to sort of rise up in this very meteoric way. So 1.34 trillion. This happened because they added compute, the stuff I'm going to teach you in this class, and then machine learning happened. And they didn't care about machine learning. They just cared about whatever somebody's got to do that's going to allow me to sell more GPUs. They didn't know whether it was going to be graph processing. They didn't know if it was going to be like, oh, maybe I'll run like Apache on the GPU. Like there's all this sort of weird things that, everyone tried to do in the beginning, try to find a good fit to sell more of these things to people other than gamers. Machine learning came along. It was a super natural fit for the architecture. They were there first. They were there better, and they continued to sort of outperform everyone else, which is why they're sort of shot up with this. Okay, so 1.34 trillion. What's another chip manufacturing company that's super famous? Apple, sort of. Apple has a commodity market that's pretty big, right? They sell. They charge me too much money for all my stuff, right? What's another company that makes only chips? TSMC makes chips. Well, what designs chips? AMD and Intel. Which one do you think is bigger? a mix of students. Historically, which one is bigger? Intel. All right, so you guys know where the story is going. Maybe you watched the video. Okay, so here's Intel. Now, I like Intel. I'm working with Intel. I do some stuff in CPU. Like, it's still super interesting. And I don't want to dump on, this purpose of this slide is not to dump on companies. It's just to give you a sense of where the world is, okay? So here's Intel from, around 2000, like Intel's way longer. If I went max history on Intel, it goes way back. It maybe could have, but I didn't. So this is sort of a similar time frame of NVIDIA. This is the last 5 years. So, it's red because it's down from the start of the thing, but it's not grown, okay? And let's say it's not grown. I mean, it was actually doing better before, before the 2020 timeframe. So they were the big dog, right? When you went to go build a data center, you went to Intel, you went to AMD, you tried to get better prices. Intel usually had the better product, and they usually won, right? It was like the gold standard for how you build data centers, and it still is for all kinds of things that GPUs aren't good at today. And they tried to create a GPU product, and it failed, and they canceled it. And I think the Intel CEO, he was here, right? Did anyone go to that lecture? Yeah. I mean, it sounds like we're kind of trying to, pivot more to manufacturing and sort of lean into this fact that we need to make chips in America and less out of the design, which fine, look, you use what you got. I don't fault the guy. But, if you ask, when he talks about it, like canceling that project and not really pushing on that project, the GPU project that really would have competed with NVIDIA was one of the biggest mistakes they made because of this, right? There was a huge market that exploded. Like Intel was never worth $1.34 trillion, ever. So right now they're worth $200 billion, which is, if you normalize it to other competitors in the field is quite low. Like AMD's more now. I think AMD's like 300 billion, okay? Because they have a stronger GPU division. That's what I like to say. Maybe they're also better in the CPU space, but there just hasn't been a lot of growth in that space in the semiconductor industry. Okay. Intel's got a lot of historic things, like they historically have fabbed their own chips. That's a lot more expensive. Like NVIDIA doesn't fab anything. Where do they get their fab done? TSMC, right? So, if China buys Taiwan, maybe this will affect that graph because it'll be really hard to get chips out of there. But I think everyone's screwed if that happens. So, maybe then Intel will make NVIDIA's GPUs. I don't know. So, this is sort of just to give you a perspective of how the world has moved in the hardware computing space and how it's not because the companies just run so much better or the people are so much better or whatever. It's, it's opportunity and, it's fortuitous, right? They built CUDA, they didn't screw it up. Machine learning came along and it exploded. Okay. Questions on this? So in the grand scope of companies, where do you think 1.34 trillion fits? This is just semiconductor industry. What are some other big companies out there that you can think of?
Apple, Microsoft.
Apple, Microsoft. How much is Apple worth? So there's some people who know. So Apple, let's see today. Apple's 2.865 trillion. Okay. So Apple's like double. Okay, but still, half of Apple's pretty good. I mean, Apple has a huge margin, a huge commodity market. For a long time, are they still the most valuable?
Yeah.
I think they're still. So Microsoft is close now. Yeah. Microsoft 1.83 trillion. Other huge company. They're a comeback company, right? They were Intel 30 years ago, and now they're all competing with Apple. But other companies you may have heard of, like, let's see, who else is on here? How much do you think Facebook is worth, or Meta?
900 billion.
900 billion, yeah, about 900 billion. So NVIDIA's worth, 400 billion more than Facebook. Okay. Let's see, what's another one? Google, yeah, where's Google? So how much is Google worth? 2.2, 1.78. So NVIDIA is like 3/4 of Google. For a company that just makes chips, this is insane, right? These other companies are, they sell high margin products. They have like huge marketing apparatus. Like most people don't know what NVIDIA is outside of this room, right? Like you go talk to your mom, she knows what Apple, like not picking on moms, like your dad, they know what Apple is. I mean, I have talked to my parents about, they know what Apple is, they sort of know what, Microsoft is, like NVIDIA, oh yeah, what's that? No, you don't know, right? Because they're sort of behind the scenes. For a company that's not like top of mind selling high margin product to customers, it's very difficult to be worth that much, and it's kind of unprecedented. And why? Programmable acceleration. Okay, why you should take this class. All right. Questions on this? All right. So what's the format of the class? Everything's on Brightspace. All of the sort of asynchronous material. We release this kind of like a month chunk at a time, primarily for the online folks who take this class asynchronously. You can watch it whenever you like. You can watch it and then come to class. You can not watch it and then come to class. If you watch it and then come to class and just sit here and be like, oh man, I already watched this, I'm super bored, then don't bother. If you watch it, come to class and be like, I'm going to ask this question that I had, do that. Okay, like make good use of your time here. And I want you to get a lot out of this class. I'm trying to create an environment where you can do that. I have this thing on breaks. I almost never am able to take breaks because I just talk too much. Anyone who's taking this class with me will know that. But I will try to have a break since we're like here for a long time, but we're not gonna have a break today because we only have like 15 minutes left or something. 20 minutes left. Okay. So I don't think we actually have a quiz this year on your background. I think you're just supposed to post it on Piazza. Is that correct? Some folks that post to Piazza this week with your background. I'm a PhD student. I'm doing this kind of research. Why I'm taking this class. It's a public note. It's mostly just so I can, see the background for people and other folks can see who else is taking the class. I noticed today that there's somebody online who's like from Canada. So, that's kind of interesting. We've never had that before. We don't get a lot of Canadian students at Purdue for some reason. Anyway, try to do that. Try to make that post. There's like some tag in Piazza about your background that you should do. Course structure, like I said, we're gonna loosely follow these textbooks. I'm not gonna make you buy textbooks, but textbooks are nice to A, guide my sort of path of material, and B, allow you something written down you can reference if you don't understand what I'm saying. So the first few weeks are going to be on programming. This is this pretty good book by this David Kirk and Wenmei Hu. David Kirk used to be high-level vice president at NVIDIA. Wenmei Hu. Who's heard of Wenmei Hu before? Nobody. He's a professor. He used to be a professor at UIUC. NVIDIA poached him. Now he works there. But this is a pretty good practical book on how to program GPUs. And we'll cover the first 5 chapters of this to give you a sense of the CUDA programming stuff. And then I've got my own book, which, I kind of wrote with my advisor and some other colleagues. It's okay. You don't have to pay for it. I'm not trying to like tote my own. I don't need your money. So you've already paid the university. So, I guess that pays my salary. But anyway, this is a reasonable reference. Some of the lecture material is based on this. We're going to go back and have something again written down to read. I think this is available for free through the libraries, maybe even online. I think they just started giving it away for free at some point. For a while, I was getting checks, like you get like royalty checks. And I got the first one was like, I don't know, a couple hundred, like maybe $400 or $500. Like, okay, that's 1 year of sales. And the next year it's like, it's $300. It's like $150, and I haven't gotten a check in a little while. So I don't know if anyone's still buying it, but eventually they started giving it away for free. What's that? It's on GitHub. So, I didn't get into this to police you guys on books. So yeah, we probably should update it. 18, that's a long time in this space, but anyway, it's there. You can take a look at it. In terms of what you're going to be tested on, it's the stuff I go through in class or in the async videos. Okay, I'm not going to like pull some esoteric thing from the book and be like, you didn't read the book. I'm going to try to be fair about how we sort of do this. Okay. Grading scheme, this is sort of subject to change, but this is roughly going to be true. So there's going to be some quizzes. They're online. They're on Brightspace. There's the programming assignment. Then there's a simulation assignment. And then we do have an exam. I've debated whether I don't do the exam. Some students don't do super well on it if they, I don't know, for various reasons. Some graduate 600 level classes don't even have exams. I justify it because I was a grad student and if nobody gave me an exam, I didn't really try that hard to, remember things. I feel like people, remember things and focus on things and actually get more out of things when they're forced to be evaluated on them. Okay. I'm going to give you a midterm. It'll be like some 2-hour thing. We've done it in class historically, but maybe I'll give you more time, but I have to do it in the evening, but we'll figure that out later in the semester. It's like 3/4 of the way through the class. So once the GPU stuff is done, we'll have this midterm. The midterm averages, some people do super well, some people don't do quite so well, which for a 600 level class is not ideal. But I give you a lot of bonus opportunity in the programming assignments to make up for that if that happens, okay? And I think it's still a very useful exercise to force you to learn instead of just sit here, drink coffee and be like, oh yeah, I understand that. I remember I took some graduate classes where that happened, where it was like, oh yeah, this is really interesting. This is so cool. And then like by next lecture, I forgot it. And then I never had to remember it again because nobody ever tested me on it. I was like, oh, that was sort of a waste. So I'd like that not to happen. So I think, and I'll give you a crib sheet, right? You can make a crib sheet to write stuff down on. Just don't try to like copy somebody else's. The purpose of that is so that you sort of do this. Again, I'm not doing this to try to create a bell curve. This is not like a 300 level, 200 level class where I have to figure out who's smartest, right? That is not my goal here. I want you guys to learn, and I think that this, at the end of the day, does help you learn. And we may decrease the weight on this and dump some of it onto quizzes, et cetera. You know, if I create more content in that space. Questions on this? All right. Okay, so lecture quizzes, there's a bunch of them on Brightspace. Paper readings, I don't know if Brightspace explicitly mentions them. Either way, I will post the paper that I want you to read in some interval on Piazza and links to it. I may create, we don't have any paper quizzes right now. I may create some like quizzes. I don't know if I'm going to time them, but just something to sort of force you to read the paper and you know, answer some questions on it. And then we will devote some lectures to discussing papers this year. You know, so basically what I'll do is like, okay, this lecture is worth material. Please just go read it. Please just go watch the async video. Instead, read the paper and come to class, and we'll just discuss this paper in the class time. I don't know how useful that will be. It's kind of the first time I'm doing that, so we'll see how that goes. But I'm going to do at least one of them to see how it goes. Programming assignment is 4 stages. We used to give these things out as just one giant blob and be like, here, do all this. And it didn't work well because everyone just put it off to the end, and then it was like way too much stuff to do right at the end. So we tier these. Do you have a question?
Is the GitHub Classroom going to be available by the end of this week?
It should have been available. It will be available by the end of this week. Yeah, there might be something we need to set it. Maybe the TA doesn't know how to.
Still goes to 404. So
okay, the link is in Brightspace.
yeah.
Okay, so we need to update the link. So yes, it should be up this week. It should have been up today, but we didn't get to it, so it'll be up by certainly by next lecture. But I'll try to make sure it's done before the end of business on Friday. Okay. Other questions? And I think that also has the descriptions of the assignments in them too, right? Because the descriptions are in. Has anyone seen the description of the assignments yet? No. Okay. So we put those in like readmes inside the GitHub repos. So I'll make sure those are released to you today, because some of you are thinking like, should I drop this class or not? And like looking at what the assignments are going to ask you to do is one way to do that. In addition to that, the TA has created an assignment 0. Who's seen this things? Some people, okay, most folks. So he posted it on Piazza. Again, get on Piazza. I'm not going to really use Brightspace to communicate. I'll use Piazza to do that. And you know, it's some basic stuff, but it's stuff sometimes when people take this class, they have no idea about. And if you look at that stuff, and some of it you won't have dealt with before, like we ask you like count memory accesses and stuff, and maybe you've never been asked to explicitly do that before, but it should be something that you can sort of intuitively figure out based on your background and the description in the assignment, right? If you can sort of take a reasonable amount of time and get through that assignment and answer it correctly, then I'm not going to say that like your background is sufficient, but it's sort of like what's the right word for this? It's like if this doesn't go well, or you're really scared, then you definitely should drop. And if it does go well, then at least that's out of the way. And you know, I'm not going to say that you're definitely going to get an A in the class if you get an A on assignment 0, but like if you read assignment 0 and you're like C++, you know, maybe you should. I'm not saying don't take the class either, because I do want people to take it. But in my experience, students who, you know, have extremely limited programming background, which can happen if you're a hardware PhD or a master's student, can struggle with some simulation stuff. If you did 5, 6, I'm fine. okay? Even if you hated 565, you're probably still fine, at least the programming side of it. But you will be expected to sort of figure that stuff out, right, in this class. And it's different from another hardware class where you just do RTL. There's no RTL here. We're only doing simulation level sort of programming. Yes.
I found a phrase for it, necessary but not sufficient.
Yes, necessary but insufficient. Yeah, good. Questions on that? So please do take a look at it if you're nervous about this. Because I don't want to put people in a position where, I have had students come to me near the end and been like, man, I'm working like full-time students who are online masters in particular. I work 40 hours a week and I come home every night and I work 40 hours in this class. And I'm like, oh, yeah. That's not what I want. Okay. And the primary reason for that is you haven't really ever debugged anything before in C or C++, or you're super slow at sort of the process for that, or maybe you're, a student who got a ECE bachelor's degree. No, it doesn't apply to people in the room really talking to the camera here, but maybe you got like a bachelor's degree 10 years ago, and then you went and worked as like a circuit designer for 20 years, and you're like, oh, GPUs are cool. And you jump into this thing and they're like, oh no, I have to code in C++. Like that can be time consuming, right? And just understanding what to do is not the hard part. The debugging and getting it to work is the hard part, right? And so if you're sort of out of practice on that, that can be really time consuming. And I don't want to put people in that position. So, and if you're super nervous or you just want to talk to me about it, come to my office hours next week. We can have a more detailed conversation about your specific situation. But my general guidance will be, took 565, you got through it, you should be able to get through this. Hopefully it's less painful. If you didn't, then come talk to me or just take a look at the assignment and assignment 0. Midterm, yes, okay. So I've said that before. So then the other part of this is going to be some simulation-based stuff. So the first programming is CUDA, how to program a real GPU. So I'll get you guys some access to some university GPUs, and you'll be able to code up CUDA programs on them and run them. And then the second part is the hardware's design. Okay, so think like Gem 5. Gem 5 studies the design. Gem 5 is a CPU simulator. You're able to add a high-level study the design of, out of order CPUs and multi-cores. We have a simulator. It's actually, developed by my group and others across, the continent, I guess. And it's like the Gem 5 of GPUs, sort of. It's arguably simpler than Gem 5, but weirder in some ways. And if you took 565, you can think of the first 3 parts of this as like the programming assignment parts of 565, where it's very structured, right? Go look at this, go change this in the simulator and measure the results and plot them for me and do some analysis, okay? So very directed. So you can go to different parts of the thing, get your hands dirty in the code, learn how to run it, learn how to collect data, learn how to plot things and analyze them, talk about the analysis, etc. That's sort of the first 3. And then the last part is sort of more like, and this is bonus, because I don't necessarily want to make all of you do this. Some of you really will want to do it, and I'll allow you to partner up if you want to do this, is a more unstructured kind of project, okay, like 565's project. But again, I'm giving you a bunch of programming to do already on the real GPU, and then a bunch of programming to do on the simulation part. So I'm not going to make it as, sort of time consuming. I'm not going to make that required piece as time consuming as the 565 part. But a lot of students do try to take advantage of this, particularly if they have time at the end of the semester, or they're wanting to get a start on research in this space and they want to poke around at a few papers and use the simulator. And, they're interesting for me to read when you guys do something that that is potentially novel, et cetera. But you don't have to do it because I know there's already a lot of work in the rest of the stuff. Questions on this? All right, no time for break. What do I have? 6 minutes. All right, so let's very quickly talk about graphics a little bit. We're going to talk about graphics like 2 times in this class, right now, and then when we talk about texturing. Okay, so what was a GPU? GPU is a weird name for things that run machine learning, right? It has nothing to do with machine learning. It stands for Graphics Processing Unit, and it basically is designed to accelerate raster-based rendering. So what's another type of rendering you can do other than raster-based for any pixel-based? Ray tracing. Okay, so raster-based rendering is how everything used to work and still mostly works, especially video games, et cetera, things that have to be super fast. we're not actually running any real physics to render the frame. You basically have this rasterization thing where there's like this 3D model of a scene. You have a pretend camera sitting somewhere, and then you can figure out like where the camera is and where the sort of view. It's called a frustrum, right? This sort of like, it looks like kind of a pyramid, but kind of chopped off at both ends, right? This is the stuff you can actually see on the camera. There's a bunch of models in there. And then we take all of those models that are in there that are basically just colors, right? It's just a bunch of, really, what is your screen? It's colors. At the end of the day, you're just trying to produce a 1024 by, whatever bunch of colors that represent what you're seeing. So you take that sort of 3D thing in that 3D space, and then you project it onto the flat area that is your screen to get a color for every pixel. That is the general process of rendering, okay? And GPUs were designed to do this and do it very fast. And it's sort of, the idea here is that they gradually became very highly programmable. So even when they were doing graphics, the early days of GPUs, they used something called fixed function pipeline. So there were like certain effects that you could do that would be built into hardware, and you could sort of like trigger them to, do certain types of lighting, shading, etc. It turns out that when you're writing video game code or trying to, create scenes that look realistic or look different or look, different from your competition, you actually want to be able to change the way the scene is rendered. Okay, so you actually go in there, and instead of just having hardware that says, I know that these are the colors in the frustum and this is the color on the screen, I can actually write code to do different things based on different lighting, based on different shading mechanisms, based on different types of material, right? So something that's shiny should produce different colors than something that's not shiny. Some things could be transparent. There's sort of all of these different, maybe you're going to perturb the actual model itself when it's rendered, tessellation, these kinds, like water, these kinds of things, right? So you want to be able to program those things. And like I said before, it had to be commodity. You had to be able to sell them for a few $100 to teenagers. And how these were manifest themselves is, basically a whole bunch of ALUs, a whole bunch of tiny, relatively simple ALUs to do computation that's parallel, and they're going to run tens of thousands of threads concurrently. Okay, so a CPU thread, what is the most threads you can get on one die for like an Intel CPU with hyperthreading, roughly? More than that. I think it's like 120 or maybe 180, right, for hyper-threaded like server class CPU chips, right? Yeah, for like laptops and stuff, you're at 8, 12, because they need the serial execution there needs to be super fast because I'm interacting with it. But Intel also sells things that go in data centers where they just want throughput, but for CPU programs, and there you can get hundreds of threads. GPUs are tens of thousands of threads, right, on every die. So obviously we had to throw away a bunch of stuff. So the name GPU today is sort of historic. It's not really meaningful because they're not really used only for graphics processing, but that's what they were called in the original days. And then there's this horrible acronym that we made to describe programming these things in a general purpose way, which is what? GPU, which is just terrible marketing. Like say that 3 times fast. But anyway, general purpose GPU, is sort of what CUDA is, right? So using a GPU to like program it to do things that are, more nuanced. All right, what are GPUs good at in terms of raster-based rendering? All of rendering really boils down to trying to render a bunch of little triangles, okay? So here is an example of a robe. So this is what would be referred to as a model if you were, making video games or 3-dimensional scenes, etc. Who's ever tried to like use what Blender is, like the open source software to like make your own models? So some folks have, right? So you can sort of go in there, like you don't have to say what every triangle is, right? The people that make the robe, like in a video game, there's a room full of people called artists that they are artists. They're digital artists. And what they do is, I was an engineer, by the way. And what they do is they have these programs. Maya is the industrial one. It's sort of the one you have to pay for. It's really good. Blender is like the open source one that kids usually hack around on. And you basically have to go in there and you can like pull on these things, right? And try to like sculpt. It's like sculpting in a digital way. Sculpt the actual, the wireframe of the thing you're trying to render, okay? And then, the software itself does this by basically making a bazillion little triangles, right? Why do you think we use a triangle instead of an octagon or something? Yes?
The smallest shape with area.
It's the smallest shape with area, right? A point has no area. A line has no area. Put a third point in there, it's got an area, you can shade it, you can make colors across that triangle. Okay, so it's the smallest shape that has in the area, so that's sort of the primitive that graphics end up using, is triangle. And so the artist goes in and they sort of pull on all of these are called vertices, right? There's basically a bunch of interconnected triangles, and where they meet is called the vertex. And then you can use that to sculpt the digital image of the sort of collection of triangles. And then if you just look at the triangles without any shading and you just colored in their edges, it would look like this, okay? And then to sort of, process this, there are many, many millions, billions, maybe trillions of triangles in any given scene, and they can all be processed in parallel because they're all basically independent operations. And that's why a GPU was designed to be super parallel, because you have to shade all of these triangles in maybe different ways. And, this is just one row. We have a scene with stuff blowing up and 50 people in robes and 10 people in armor, right? You basically have to shade all of their little triangles to find the final colors for the scene itself. And then if you heard of frame rate, right? Frame rate is basically like 60 hertz is usually what 120 hertz, right? If you're doing like, high-speed TVs, et cetera. This is how frequently the screen is updated. So at every 6th or every 120th of a second, we're completely re-rendering everything on the screen, right? So you clear out the whole frame buffer. Frame buffer is basically just the big buffer that stores all the colors. And then you completely redraw the screen. Why? Well, because maybe the robe blew up in the last 60th of a second, or maybe the camera moved in the next 60th of a second. So you have to figure out what the next scene looks like. So I have this super parallel, consistent demand of every 60th of a second, give me a new bunch of colors. And that's what the GPU does, okay? Questions on this? We'll finish this off. Yeah, we'll come back and finish this off on, I guess, Tuesday next week. Take a look at the videos if you want. I'm probably super behind where we're supposed to be for week 1. I don't think there was any more. Yeah, this was all there was no like logistic stuff here. So anyway, this is generally how this is going to run. Maybe you enjoy this, maybe you don't. I hope that you do. I like lecturing through this class, so sort of keep coming, and I'm not going to require you to watch any videos at this point. Okay, we'll just sort of keep going through the slides. I might pick up the pace a bit now that I only did 20 in like an hour and a half. So, but other than that, that's how we'll go. Okay, questions? Thank you. I will see you all on Tuesday. Thanks for coming.